Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Leonid Petrov and Yuri Kovalev with us today. Hello, Leonid. Hello, Yuri.
Hello, Frank.
Well,
And Leonid, let's start with you. What's your geolocation?
my geolocation is 38 degrees 59 arc minutes 45 seconds latitude, 283 degrees or 8 minutes 57 arc seconds longitude, and 37 meters above reference ellipsoid.
Okay, you are awesome. Very good. And for mere humans, that's actually probably somewhere around Maryland, Washington.
That's correct.
Oh, very cool. And Yuri, what's your geolocation? Dare
Hello,
I ask?
everyone. I'm right now, I am located in Max-Planck-Institut for Radioastronomy.
Fun.
And this is actually not enough to guess where I am because Max Planck for Radioastronomy is located in several places.
Okay.
And one of them is in Bonn. So I am right now in Bonn. But there is also another place, I would say even more fun, which is in Effelsberg, where we have a 100-meter large radio telescope, which is the biggest one in Europe.
Cool.
Fully steerable. Unfortunately, we cannot say anymore that it is the biggest one in the world because the GBT is slightly bigger.
Yes, unsteerables. Yes. Very cool. Very cool. Let's see. So it is February 6th, 2025 as we record this. I'm in Phoenix and we are already warming up into our spring, early summer kind of weather. So we're already heating up. And how about in Washington? Is spring in the air? Are the cherry blossoms starting to do their thing?
No freezing rain, so weather is not favorable for
Not
observations.
yet. Not yet. How about in Bonn? Is spring happening? Or are we still in our winter mode?
I feel the spring. I'm not sure if the spring feels me. So we are sort of, still expecting the spring to come, unfortunately. My wife worries that her flowers will die if it continues for a few more days like that.
Okay, well, we'll keep our fingers crossed. It'll warm up. It'll be good. In Yuri, as long as we're there, what do you like to do for research?
So we start from me.
Sure.
Okay, so I am an astrophysicist. If you want to put a label on me,
Okay.
which is probably wrong, but it is the shortest way to describe it. So I like to study active galaxies.
Cool.
This is probably the most using whatever you can learn from them in all electromagnetic bands and even using particles
Yes.
since recently. So what is called multi-messenger astronomy.
Yes. Very cool. And Leonid, what do you like to do for research?
I'm a geophysicist and I work in space geology. That's why I know my
Yeah, I was
geolocation
gonna say.
precisely. And not only my geolocation of my desk, but also geolocation of observing stations.
There you
And
go.
my duty is to measure them with sub-millimeter level of accuracy.
Cool.
And in order to reach that sub-millimeter level of accuracy, we need to measure them with respect to something which is very remote, very stable, and it is the subject of our paper.
Cool. And that is
Frank, I wonder if I can sort of break your properly thought through way of how things are presented
okay.
and underline that actually the title of our paper is short and the last word is astrometry. And I think that you have already realized that neither of us has called himself an astrometrist. So
Yes.
it means that both of us have no idea what this paper is about. I guess this is to stop this recording.
Well, that'll do, everyone. I hope this made your day. We'll move on to the next one. Bye.
But we are trying to learn.
Oh,
Yes.
very good. Very good. Okay, let's go ahead and get into this very awesome article from two non-astrometerists. Okay, and we're going to do the full screen. So, it is open access. It's the open access era, people. You can go grab a copy for free. Go get one. The Radio Fundamental Catalog 1, Astrometry. And Leonid and Yuri, take us away.
Well, to achieve the goals of space geology, and the goals are to reach millimeter level of accuracy, we need a grid of several hundreds of bright extragalactic objects. So that's original motivation of the study is to have what we bear in mind from the very beginning, practical application. Second, if you go to space for navigation, you need to have at least several thousands of sources with respect to which you can navigate. And it's important because navigation error may cost hundreds of millions of dollars in damages, which one of the lessons which at NASA we learned a decade ago, that even if you have very precise navigation, you need to have a tool to check. And that's what's the second motivation. And the third motivation is to provide a grid of sources with precise positions for our fellow astronomers. Okay. Because nowadays most of the observations are performed in so-called noding mode, when the array telescopes turns on a target, which is goal of observations, then moves to a calibrator and back.
Got it.
Cool. So, and if you know precise position of that calibrator, you can get differential astrometry. For instance, you can measure distances to pulsars. Also, you can extend integration time beyond the limit set by atmosphere, so you can detect weak targets. So that's original motivation of that study, was to provide that grid of calibrators as a service to the community.
Nice, very good.
If I may here add a little bit more, this differential astrometry is used truly very often for many different applications. Today, Leonid already mentioned measuring distances to objects through parallaxes.
Right.
I just wanted to say that, guys, even as cool as testing the general relativity, you can do it through differential astrometry, a very important technique. You can do almost anything with it. Thank you.
Very cool. Good. Thanks for that.
And when we started observing program, we also realized, when we get a large list of targets, you can modify slightly program and try to focus to reach completeness of your sample. Because if you have a complete sample, you can generalize your conclusions made from sample for entire population. So that another goal of our study, to provide a complete sample sense of compact radio sources. Okay. And this presence of this availability of that samples allows to make a number of other interesting studies.
Cool.
Yuri can mention about.
This is still introduction, and allow me to add a little bit of personal touch on this.
Please.
The reason why Leonid managed to, what's the right word? Let's use the word convince me to invest a huge amount of my not only scientific time, but also of time which was stolen from personal life into this project, starting from the year 2003. Was exactly this idea that in astrophysics, if you want to to understand properties of your objects, of your astrophysical objects on the sky, you need complete samples. So you should avoid having biases when you miss certain kind of objects, you miss certain groups of objects in the sample, in the group which you study, and then you risk making wrong conclusions. So originally, for me, was the reason to get involved in this project, and for already more than 20 years, we are doing it together.
Very cool.
And since you mentioned a little bit his personal reason, which prompted him to join the project, I should mention when our first conversation with Yuri in 2003, he approached me at the conference and asked, is it possible to observe a list of sources which his father, Yuri Kovalev, started to observe in 1978.
Cool.
And that
Cool.
we observed that sample, and it allowed to make connection between work of his father and work of the son. But it took, and fortunately, it worked, although this work took a significant amount of time. Fortunately, his father is still working, is still good health. He was able to see results.
Oh, that is awesome. That is so awesome. Very cool.
Yeah, I will start crying, so let's move on.
Well, that would be a first, but okay, very good. Yeah, this topic works on different time scales. So it can be generational. It's not like transients, right? Where you're up and down in a minute or something of that order. So, very cool. Very cool. I love it. Thank you for sharing that. Okay. Onward.
We can scroll down a little bit.
Okay. Let's see. We got our observing campaigns, and we got some of the dedicated experiments, and we talk about some of the experiments, and then we get to this long list of observational programs.
So observation started in August 12, 1994,
Mhm.
and the original goal of first campaign was to get a list of calibrators for support of VLBA. So that's original goal, and then with time, this program evolved, and in our analysis, we took all the data which are publicly available, which we were able to find. So, so in total was 72 programs. You can scroll down.
Yep.
And some of these programs we
Leonid?
designed ourselves, me
Leonid.
and our colleagues. Some of these programs were designed by others. With some authors we closely collaborated. Some PIs we did not know in person, but we tried to took all the data from all campaigns, no data point left behind.
Okay, cool. Okay.
I would like right now to interfere for a second,
Please.
And say a few. I will try to say, truly very positive words about an approach which is getting more and more traditional, more and more common in the modern astronomy.
Okay.
Approach of making results of observations publicly available.
Absolutely.
Relatively soon after observations have happened.
Mm-hmm.
And this is similar to what you have started, our whole discussion today. You said to everybody, all right, guys, go and download the paper because it is open access.
Yes.
The same is true with the data which we have observed with Leonid, as well as the data which many of our colleagues have observed, are all publicly available. So it is extremely important because this allowed us to take all the data and to get out the most from it. All right, talking about the completeness of the samples, talking about accuracy of presented results, just using everything what was done.
Yes.
Allowed to get the best outcome, and that is why later I think Leonid will claim that this is the best and most accurate catalog to date.
I will not argue with that.
But it also allows other people, all right, to take all this data, including our data, to check on us and to do something even better.
Yes, very good, very good.
In all our programs, we waived proprietary period. And there were certainly, although we make a first analysis, we try to do it very quickly, but final analysis was delayed. And since data were publicly available, we know that was a number of colleagues, other approach to us.
Oh,
they
yeah.
took data from archive, and they found observations of their sources, published the paper, and we are very pleased that that happened. And also, we're also pleased that later there's we set this policy between us 20 years ago. Now it is became mandatory for all NASA projects.
Yes, yes.
So we just ran before the locomotive.
Yes, yes.
We were very pleased that it's nowadays becomes mainstream because we benefit ourselves from that, and our colleagues benefit as well.
Absolutely. So that's a good plug for open science, whether that be open data, whether that be open access to articles, or whether that be open access to the software tools that you need to make that happen. So good shout out. Yep.
So the data set comprised of 72 dedicated campaigns. So in total, I collected 66 petabyte of data, but we did not handle ourselves. It was this data handled by Observatory. And after correlation, we got about 140 terabytes of visibility data, which we handle ourselves.
Cool.
But not enough. In addition, we also use all geodetic VLBI data.
Yes. Okay.
And in total, about 200,000 hours, and we process them data together. And from this, and we benefits for our scientific goals from the synergy of astronomical observations and geodetic observations.
Excellent. Very good. We used all of them. Nice. Cool. Okay. Onwards. Where shall we go?
Let us keep scheduling observations because it is maybe too technical.
Nothing's too technical.
And jump to data analysis.
Okay.
I can tell you something which is not too technical, which will make many people excited because Leonid might be too shy to tell that. But in order to use the most efficiently the observing time of VLBA, Leonid has written a tool which allows VLBA operators, when they have several hours of free time, to approach his special software to just put the time interval, and then his software will generate automatically on the fly a schedule for VLBA to observe. Thanks to that, actually, the experiments which were led by Leonid got more observing time than they actually asked for, because it allowed to use the VLBA observing time the most efficiently.
Nice. Very cool. Congratulations.
Yuri is correct. Automation is a key because without automation, we would not be able to finish that.
Have that kind of the result that we have here, right? Yeah. Very cool. And here's our software, Pima.
So the first stage of data analysis is done by observatories, so that they transfer data. By the way, what is the data for VLBI data? In literature, often we can see incorrect statements. Data are voltage. So we process trillions records of voltage, and this voltage from stations is noise. So it defies this vulgar dichotomy signal and noise, because all these results which we discussing today are produced from noise.
Yes.
And this noise, the dominating noise is thermal noise from the receivers, with some admixture of noise from our target sources. But why we can extract information? Because this noise correlated. So the first stage of that analysis is correlation. Okay. So which is performed by correlate. It reduces size from 66 petabyte, which is even today is unbearable. And after the processing, this media is reused. You don't need this petabytes of data, and then the correlator they compute out and cross spectrum of cross correlation.
Yes,
and that is input for further stage of data analysis.
Okay.
Leonid, I think it will be interesting to tell what is the typical value of the correlation coefficient which contains the signal.
Typical 10 minus 4, probably more typical. That is ranges from 10 power minus 5 to 10 power minus 2 to 10 power minus 4 is typical.
That is why we are saying that most of this data is noise, because the signal is only a small fraction of a percent. Everything else is the noise which we, to simplify, throw away by performing this correlating process.
Yes. Okay. Thank you.
And for data analysis, we have to develop our own software, which took significant time. So the code base is over 1 million lines of code.
Wow.
Just recently, it became released as open source just several days ago. Unfortunately, not during time of publication
But it's out there now, so okay.
Yeah, it's now officially released. So it has first stage is a fringe fitting.
Okay.
So that so then we process records of
Right.
cross correlation, and we find a group delay, phase delay rates, and as a byproduct get phase.
Okay.
So it is rather time-consuming procedure. In total, it took over 4 years of work time at computers, which we had at our disposal.
Nice.
We don't have access to supercomputers.
Wow.
And after that stage, we go to second stage, we call astrometric or geodetic analysis.
Okay.
Leonid, I think that right now or later we should explain how the phase, which is the most important for astrometric analysis, is not degraded, but how much and why it is affected by different effects. So do you want to discuss it now or later? So because when you perform this fringe fitting, you sort of solve for all these different effects which affect the phase.
Maybe a little bit later.
Okay, but we shouldn't forget about it. Okay, thank you.
So next step, after we computed group delays, we process group delays. Why group delays? Phase delays are more accurate. Phase delays are ambiguous, and atmospheric fluctuations are makes phases useless.
Yes.
So to overcome that, it was suggested at the very beginning of the OBI in 1970s to use group delays.
Okay.
So at a group with a wide bandwidth, group delays becomes very precise, and we process group delays. So most of the analysis difference between group delays and phase delays is small, but there are some effects which essential. The difference between group and phase delay becomes essential. So for modeling these observations, we need to have very sophisticated model which accounts effects on the millimeter sub-millimeter level. So I will not go into details because it is paper about astronomy, not about geophysics. But in particular, we have to take into account such effects as crustal deformation caused by variations of atmospheric pressure.
Yes.
Caused by storage of land water. We have to learn how to model partially in the atmosphere, and we use output of numerical weather models which are run here at NASA. These are the same models which also used for weather forecast.
Okay.
And before other effects, which let me skip all these technical details. So we have very sophisticated model, and it is the same model used for geodetic applications.
Yes.
It's essential because with the accuracies which we are dealing, it is on the sub-nanoradian levels. We need to count all these effects on the level 10 minus 9, 10 powers 10.
Cool.
Leonid, let us remind our viewers, you have mentioned that in order to measure the group delay with very high accuracy, we need to observe in the wide band. So what is the band? And so the typical observing frequencies or observing band, which is used for the geodetic and astrometric observations, is between, to simplify, 2 and 8 gigahertz.
Right.
And the wider it is and the better it is covered by our measurements, the higher is the accuracy. And
Okay.
probably I would add right now that unfortunately, the lowest part of this band, 2 gigahertz, becoming less and less usable, or probably I would even say almost unusable, is almost unusable right now because of more and more radio frequency interferences,
Yeah,
which are generated right by human beings. And right now we are sort of, and astrometry as well, are moving to higher frequencies. But originally, for many years, and the data used in this paper, right, they come from 1994 and later. They have used the whole band at the times when 2 gigahertz was still okay. And you can think about, so 2 gigahertz, even your microwaves
yes,
and Wi-Fi and mobile networks are located in frequency close already to us, and this is a problem.
yes. Okay.
Yeah, Yuri mentioned observation at two frequencies. It's essential for getting the highest accuracy to observe at several frequencies because contribution of ionosphere. Contribution of ionosphere is frequency dependent. So observing at the two widely separated, two or maybe more, there's some observations make on 4 frequencies. On widely separated frequencies, we can compute ionospheric contribution.
Yes.
But what if
Okay.
we are the observing campaign was done at 1 frequency, or we can observe at 2 frequencies, but we detected a source only at 1 frequency. And this is a novelty which we introduced in this study. So correct dealing of situation when we have only 1 frequency. There are 2 cases. One case when we have a dual band observation missing, so we have dual band campaign, but some sources we detected only at 1 band.
Yes.
Usually at low band, just because we didn't have enough sensitivity. So and that case we use total electron contents from GNSS maps with adjustment. It turned out that accuracy of GNSS atmospheric map is not sufficient for this demanding application. But we used the fact that a significant fraction of sources we detected on both bands, and so therefore we can use tech from VLBI data themselves when it's available to tune GIM. And so turned this approach allows significantly reduce atmospheric errors. In the case when experiment was once single band by design, well, I think we have several cases when second band failed because of technical issues. So in that case, we can't use that approach. In that case, we are still using correction from GIM, but we compute rather sophisticated stochastic models to account errors of group delays computed from GIM.
Okay, I'm with you. I'm good. Yep.
We can go to the next page, parameter estimation. Page number 12.
Small. Okay, I'm with you. All right. Parameter estimation.
It's essential for our approach that we process all the data in one single least square run.
Yeah, right.
It provides significant advantages because in that case we treat all the data uniform.
Right.
It's essential that it also allows us to estimate parameters of the instrument. But in this case, instrument will be entire Earth, all array of all the stations, because we here deal with absolute astrometry. For absolute astrometry, we determine both position of the sources and orientation of the instrument.
Yes.
In that case, instrument it will be in generalized meaning of this word, because instrument will be array. So we need to model very precisely motion of the array. That's maybe explains why a geophysicist dares to go into this this business. So we have to model environmental effects, residual atmospheric path delay after we compute a priori path delay from numerical models which are run here at NASA. Just 400 meters from my office.
Nice.
We also have to estimate rather sophisticated models which accounts for linear and non-linear station motion. Linear motion, it is mandated to plate tectonic. This is a major component. For some stations, they have uplift due to tectonical motions, or for instance, in the Fennoscandia, this uplift due as residuals of the glacier which melted 10,000 years ago.
Okay.
But crust still has memory, is still uplifts.
Yes.
So of course we have models seismic motion. This is jerk. After jerk, for some stations we see relaxation.
Okay.
And,
interesting.
we also have to precisely model Earth rotation. So for Earth rotation, we use the empirical approach. So when we estimate Earth rotation as a sum of two, especially into two bases. You can go to the next page.
I'm with you.
On the bottom of this page. So it is basis of harmonic basis. So which accounts for harmonic motions, which is comprised of notation, is so-called high frequency orientation parameters caused by tides and other phenomena.
Yes.
And also irregular path, which a major contributor is atmospheric angular momentum. So motion of mass, changes of the pressure, that drives irregularity of rotation, and we have to count. And novelty of our approach, we use expansion into a basis. And this was very essential because we processed also data which were observed in configuration which is not favorable for determination of orientation parameters from the same observations. But we used all genetic observations which both before or after. You can go next page. It will be, you'll see a figure.
There we go.
This example. So here this green green line. This shows a time when there were geodetic observations. Upper small blue, it was additional so-called intensive sessions, and in the bottom a red square, this is observing session for astrometry. Okay. So we benefits, and you see also gap, it is gap because of weekend, and so we benefits this overlap between geodetic observations and astrometric observations.
Yes.
And repeat this uniformly. This is novelty of our approach with respect to we ourselves and our colleagues tried in the past.
Got it.
It allows us to elevate this situation when we when observation itself are not sensitive enough. I mean, astrometric observation not sensitive enough to be there for errors in the Earth rotation parameters may contribute to sources, but we combined all the observations, and the combined geodetic and astrometric, they don't have that problem.
Okay. Good. I'm with you. Nice.
It's essential when we solve for least square problem and solve for station position, source position, we have a system of incomplete rank. So therefore, what's the origin? Equations of wave propagation are differential equations. So there is a constant integration, and this constant integration is arbitrary. We can rephrase it. The base of physics or law of conservations, which are related to a symmetry of space-time. In particular, all laws of nature are independent from translation and rotation.
Yes.
So therefore, it's impossible in principle to determine absolute orientation or origin of coordinate system. So we have to somehow set it. So it is done by constraints. And these are called minimum constraints. So it means without these constraints, you cannot get the solution. You can get only family solution.
Okay.
But addition, we have to impose some other constraints, which goes into several categories. So some constraints are decorrelation, because some parameters may be correlated, and we need to decorrelate. And some constraints are stabilizing. And it's essential. Our solution depends not on the observations, on the constraints. And we disclose all constraints, because we know in the past there were problems when we're reading some of these papers. Maybe even somebody can talk about our papers, that information about constraints is not revealed in full details, and this makes it difficult to interpret. So we put here in several pages all details about all constraints, and totally declared similar way like all taxpayers have to declare their income in 2 months when they prepare tax return. So using the same logic, we disclose information about constraints.
Okay, very cool. Good, I'm with you.
So we can go to page 16.
Yes. Constraints. There we go. I should have slowed down a little bit there. Okay, very good. I'm with you. Okay, good.
Go to page 16.
And let's see, 15 are decorrelation constraints, and then 16.
Yeah, and going to outliers, filtering of outliers. So without filtering outliers, that data themselves would be barely usable. So that's there's a number of reasons why I have outliers. No, first obvious. It's when we try to detect weak sources, data situations, then detection is uncertain. It depends on signal-to-noise ratio. Signal-to-noise ratio in this context is the ratio of amplitude to the mean noise. So if a signal-to-noise ratio more than, we could put 7, this is almost certain detection, and we can compute the probability of false detection. This will be very small. On the other side, if SNR is low, like 5, probability of false detection can be on the level of 30%.
Okay.
So we want to squeeze the most from the data. So therefore, we go into the area when detection is uncertain. And turns out it is possible to do it when if we consider both geodetic and astrometric data.
Yes.
Because if we run a solution from definite detections, they have scatter which related to the thermal noise and systematic errors, which is typically on the level of tens picoseconds.
Okay.
So there was no detect. It has uniform distribution within search window, which is typically several microseconds, or depends on observers, from 2 to 60 microseconds.
Okay.
And it allows us to separate these two populations. It requires some sophistication, but we can do. And this paper we explain how we did it. So first we makes a solution with strong sources, and then gradually we add sources with a low signal-to-noise ratio.
Yeah.
And essential that we also implemented automatic procedure of outlier elimination. It's essential. Without an automatic procedure, we would not be able to process data. This is based on the lemma of inversion of extended matrix, also known as a Sherman-Morrison lemma. This is highly efficient algorithm which was developed for different purposes of processing genetic data, but it became a cornerstone of processing astrometry data.
Right. Cool.
I would like to add here, so the software which is being used here,
yes,
it is open access, as we mentioned already, and it is known to treat the errors in the most accurate way, the errors which are related to processing the data from very long baseline interferometry. And because of that, the same software were used by us in another project for the ground to space very long baseline
Uh-huh.
experiment, which was called radioastronomy, because there you always measure a weak signal,
Yes.
because the rest of the signal which is left for a huge interferometric baseline between ground and space, the signal is always low. And also, as Leonid said, there is no way you allow yourself to throw away the data.
Valuable
You,
data.
you truly need to assess if it is the noise or the signal. And the same software with certain uh, was used, basically the same software was used by us to assess the probability of false detection
Yes.
of signals from the space, also from space will be observation. So it actually has quite wide applications, and all around the world this software and this approach was used to assess qualities of space field B observations.
Beautiful, beautiful. Okay.
During alpha elimination, it also have reciprocal process restoration of the observations which were eliminated in the previous steps. So this two-way process. We also update weights which accounts for unmodeled effects. In addition to just a simple alpha elimination, we also have to revisit for several cases. In one case, this process for weak sources may converge to solution which throws away all the data of a given source. In that case, we have manually intervene and examine point by point source, point by point, and in many cases we are able to restore.
Okay.
Also, another case is a source with several companions. We call it visually double.
Yeah.
Sometimes even more companions. In that case, may happen that the process of fringe fitting, some observations got one companion, for some observations it had different companions.
Oh, yes.
So it's the special procedure of called companion separation. So so that we split the pointer to the data. We don't touch data, but we split pointers and we create two sources from two records for the same data, and we can get positions of two, sometimes three sources in the field of view.
Okay. Cool. Wow.
Let's go to page 18.
My goodness.
And
very impressive.
What we introduced new with respect to prior analysis, so concept of fused solution, fused data. As I mentioned, in the case if we have observations of only one band, either by design or by missing data which were not detected, in that case we can compute an atmospheric contribution. But what's critically important, we also compute uncertainty of that atmospheric contribution, because if we do not do that, we would have bias towards that part. It's essential, and after we spent a lot of efforts. It was separate paper preparation to that paper. We published two.
We'll come back to that.
Papers, which we got into validation of our stochastic model for residual atmospheric combination. Okay. After that, we can combine all the data. We call it fusion. All data from all bands, all programs, no data point, they are behind. Yeah. This is novelty of our approach, because we are able to use all the sources, even sources which we observed in one band, and we found and we ran tests, we will show later, which shows that uncertainty of single band solution are realistic.
Cool, I'm with you.
So let's go next page. There were some tables.
Yes, here's our first table.
Let's go to table number 2. So that gives some statistics. So fused solution dual band.
Yes.
And solution of bands, S bands 2 gigahertz, C is 5 gigahertz, X band 8 gigahertz, and K band 23 gigahertz.
I'm with you. Yep.
And here, but it gives also number of observations. So you see that we were able to restore 4,000 sources. For which we do not have dual band observations.
Impressive.
So that's novelty of this data analysis with respect to what was done before. But if you scroll a little bit down, so it gives general statistics, which also accounts table 3. It also counts geodetic observations. So we have much more geodetic observations than astrometric observations, but geodetic observations targeted only a relatively small subset of sources.
Okay.
0% or so, but very extensively. So in total, with over 200,000 hours.
Wild. Okay.
Then the rest, so next sections is about error analysis. In general, astrometry, it is a science about our attempt to evaluate errors. And in my view, if to consider written a history of astrometry when we try to do it, and we try to do it probably after works of Bessel and Gauss from 20th, 30th, in 19th century for 200 years. In my view, we still didn't get satisfactory work. And we do not claim that we solved that problem in our paper, but at least we tried our best to approach to realistic estimates of our errors.
Okay.
And, the first approach is terrible word decimation. I think nowadays, in modern language, it doesn't build this terror which it brought 2,000 years ago in the Roman Empire.
Right.
So it is in the decimation we remove a subset of points and to run several independent solutions and compare with them each other.
Right.
So in the case if errors uncorrelated, then doesn't matter which way we decimate, but we anticipate about notion that errors uncorrelated is non-physical, and I don't know processes in the nature which are uncorrelated. They're always correlated, and when we have large data sets, correlations start to play pivotal role. In the presence of correlation, order of decimation matters.
Yes.
And it is simple decimation, we call local, is just even, odd, even, odd, even, odd, even. So so we split data into two data sets in the chronological order of observation.
Okay.
Other approach, we can go next page.
Okay, I'm with you here.
Is to split chronological order to split into two subsets, first and last, FL.
Yes.
Again, if data uncorrelated, we can expect that this decimation will produce the same result.
This is local. Okay.
It's not.
Okay.
Let's go to page 21.
Okay, page 21. We got some
Page 21. So what we did. So well, if we go a little bit up, this previous figure of number 4.
Figure 4.
So here, let's go a little bit look, focus on the left figure. You can zoom it out because they're basically very similar. So here we compute a histogram of normalized source position errors in this right section, and on the right will be declination.
Okay.
So so we just divide position errors by uncertainty.
Okay.
And the distribution. And that's green points.
Yes.
And, in the case if we accounted our errors correctly, then it should be Gaussian distribution. This is a smooth blue point in the middle.
Right. Right.
You see, we have deviation. So that's so therefore it means that our stochastic model is still not precise enough. So a general approach which was done in the past and also we did ourselves is to make rescaling errors. Well, we can think, but since we don't know why errors are wrong, so therefore we can so therefore we can think about very simple model. A very simple model is additive and multiplicative. So additive model. So we assumes that errors are underestimated by some constant, which we should and in quadrature, it is additive
Okay.
term. Multiplicative term, this errors can be scaled by some factor, multiplicative. And and in the past, we applied both factors. Multiplicative factor, which we found from by processing genetic data, and additive factor to reconcile errors.
Okay.
So now you can go to the next plot on the same page.
Yeah,
You can show us all 4 plots. So that we started to tweak with our results and apply multiplicative and additive model correction to our errors.
Yes. Mm-hmm.
And consider two cases for decimation, what called local decimations, odd, even, and global, first and last.
Yes.
And we see results are very different. So on the left part, we see local decimation, odd, even, for at assertion and down for declination.
Okay.
So what does color plot mean? So we try on the grid scale and flow and fit it and check this RMS of the difference with respect to Gaussian distribution.
Right.
And the calls and computed deviation. So this the bluer color means the smaller deviation. And it does just not to make this plot readable. We cut off at signal to noise ratio 2.
Okay.
Just otherwise the plot will be unreadable. So we see if decimation is local, odd even.
Yeah.
They're very different from global.
Yes. Mm-hmm.
And this is our interpretation is a manifestation of correct errors. That means that if we compare data which are close in time, we have one errors, and we compare this data which are on the which has a larger scale on the time difference.
Okay.
We have bigger errors. That means that there are errors which increase with time.
Not what we want.
And since the goal of this work was to provide positions which are average over all observations and provide global reference, we adhere that it's essential to rescale our errors according to global decimation.
Okay. All right.
And we claim that this makes our solution more realistic, our errors more realistic.
Okay.
And if you go on the same page, scroll up, you will see and the plot red dot. This red plot after
you've gone through this. Okay.
After we apply error rescaling. So we see that became much closer to Gaussian distribution.
Closer.
But much closer.
Mm-hmm. Mm-hmm. Yeah.
So
nice.
let's go to page 7.
Especially on the tails. Mm-hmm. Yeah.
Yeah.
Okay. Page 7.
Oh, sorry, figure 7, next page, page 22, sorry, page 22, figure 7. So here we estimate what we also found that for route session declination, so when for sources with large errors, this scaling factor converges to is 1.08, 1.16. So it means becomes independent on errors. But on the other side, if we have sources with very small uncertainties, that becomes some oscillations. So our interpretation that this scaling factor is describes processes which are independent on statistic of our sources, and we apply the scaling factor. For remaining uncertainty, we computed additive factor.
All right.
If we can jump to page 23, there are several plots of these additive factors. Page 23.
Page 33. Where are we at? 22. Let's slide down to 33.
23, yeah. On the top of page 23.
Getting there. Getting there. This is a big long article, people.
Page
It's APJ supplement. Oh, beautiful, beautiful, beautiful.
Oh, I think Leonid was talking about 23, right, Leonid?
23, 23.
23, yeah, 23.
23.
23.
Sorry.
Sorry, my bad. We'll still get to that lovely thing.
There is still hope, yes.
25, 24, and 20. One more. 23. There we go. There we go.
A little bit up. There's a figure 8 before. Yeah.
Yep.
So what we did, we investigated how this error flow depends on anything. In particular, what we found is this depends on the declination. On the left part, it is for right ascension. On the right for declinations. So it's error in right ascension, error in declination. Each function itself depends on the declination of the source. We see that for right ascension, we have oscillation. We don't have explanation of what is origin of oscillation, but it varies on a level from 50 to 100 microseconds. But for declination on the right plot, we see it systematically grows with declination.
Okay.
And essentially that even for a relatively high declination, 45, 90 degrees, it flows at about 100 microseconds. For declination, south hemisphere, it rises to 200 microseconds.
Okay.
It's a little bit disappointing because that's when we apply this reweighting, error increases. So we can get formal errors, which we neglect, or correlations. They're very small, and there is a general, I call it student syndrome. So if you have very small errors, that is great, and people like to report them. But downside, this is very small but not realistic. And what's essential for both for applications and for science, maybe for science even more important, you have to have realistic errors, because eventually, goal of scientific research often is reduced to test of hypothesis. Right. And if you don't have correct errors, your hypothesis test may be skewed. So therefore, we applied, although we're not very happy that we have this flow, we applied them for our data, arguing that since it's a global data set, we have to apply this error flow from this global decimation. By the way, if you do local decimation, there will be different error flow.
Yes.
And plot is scroll a little bit down, shows distribution. Scroll down with these two plots. Yeah, shows the distribution of normalized errors. This is after final reweighting.
Very good. Cool.
We are quite satisfied. We are not satisfied with the fact that we have to apply relatively large flow. We're not satisfied with that, but we're satisfied that we can claim that our error model is realistic.
Okay. Good.
Cool.
Very cool. Okay.
So I have to skip some other parts. Let's go to figure 17.
Figure 17. These are some of the differences. Figure 17.
It's a comparison with
normalized distribution.
It's page 26. Yeah, it's comparison with Gaia. Gaia is, we have only one technique which can provide a position with comparable accuracy. It's Gaia. So therefore, of course, we immediately computed differences between Gaia and
Leonid, why don't we say a few words what Gaia is, okay?
Yeah.
So we are talking about a European or European-led space mission,
yes,
which has observed more than 1 billion of objects in our galaxy in optical band, and more than 1 million of objects from outside of our galaxy, right? So other galaxies. And thanks to the fact that this optical telescope was launched from Earth, it does not suffer from the Earth atmosphere. So it is extremely important. We all know that when we go to enjoy the wonderful night sky, we can see that all the stars are sort of flickering, right? And also due to that, when you use an optical telescope on Earth, if you don't use a special techniques to compensate for the atmosphere,
Right.
all of your objects on the sky in optical band will look 10 times larger than they actually should be, even more than 10 times, due to these fluctuations of the light and optical in our atmosphere, optical light in our atmosphere. And so when you launch it into space, your picture is much more stable, and due to that, you can measure positions of your objects with absolutely unprecedented accuracy, and basically having like single optical telescope in space.
Yeah. Right.
The Gaia are two telescopes, but let's call it single telescope.
I
You
get it.
can get accuracy of position determination in optical band from space comparable to what we can do from the ground using very long baseline
Yeah.
interferometer.
Yep. Very cool. Nice.
So in fact, when Gaia first data were released, we downloaded them within half a day and ran comparison. And we found very interesting phenomena, so that for a fraction of sources, about 15% of the sources, there is offset between Gaia and VLBI, which has astrophysical origin.
Okay.
But it's the subject of other papers. And so therefore, we in our analysis with Gaia, we removed these sources which had a significant offset along the jet. But that here we computed the histogram of the differences, of normal differences between matching sources. About 60% of sources from our catalog has a matching source, a matching counterpart with Gaia.
Okay.
So we can we computed arc between Gaia and VLBI, normalized by these errors, which accounts both VLBI errors and Gaia errors, and compute distribution is a green line. And in the case if both catalogs don't have systematic errors and the uncertainties are computed correctly, there should be the distribution should be relay. This is smooth black line. So we see deviation. It is, and in fact, this deviation is become closer to relay than in the prior work. But nevertheless, it's interesting. What is the origin? Is this because, despite we made our big efforts to have realistic errors, maybe we still didn't account for something?
Maybe you missed it.
It's called a little bit down. A little bit down, yeah, with this plot. So what we did, we just tweaked. Okay, we have a very model which we think is very precise. Our error model. Let's a little bit add additional variance, and so let's employ some scaling factors, 1.2, 1.4. So this is what you see. There's other lines, blue and red, 1.2, 1.8.
Got it.
1.2, 1.4.
Unknown error, but
when we put the scaling factors, if we disagreement with relay and distribution grows. So that allows us to set a upper limit of correctness of our error model, 20%.
Right.
So our model and also Gaia model. So that means that we are confident that our errors, if they are underestimated, but no more than 20%, which is essential. But we went further. If you scroll a little bit up on the right hand side, on the right hand side. So we make this plots for subset of data using statistics which Gaia reports are called chi-square degree of freedom.
Yes.
So there are some sources with excess noise. So we split it into several subsets, sources with chi-square degree of freedom less than 1.1, in the range 1.12 and more than 2. And we see
Yeah.
so then when we select sources with Cascade green from Gaia 1.1, it is green lights. This is agreement is the best. And when we select sources with Cascade freedom more than 2, we have rather poor agreement. And here we can indicate that that these are problems with Gaia. At least we see for some sources. And also just for completeness, I will not spend much time here. That's it's written in the paper. We will also were able to identify some declination bias in the comparison with Gaia small on the level of 80 microsecond, which we attribute to our errors.
Okay.
But
Fair.
so that we can see both deficiency of radio catalog and deficiency of Gaia.
Right. Which is very valuable.
Next session about impact of source structure. So let Yuri talk. I'm a little bit tired.
Okay. Yeah.
I also wonder about our viewers, if they're still alive, but before I move to...
I'm still alive. That's all that matters.
Still, I want to, if I may, to repeat what I typically say to my students, and they are mostly in astrophysics, and I tell them, you know, your colleagues who do astrometry and geodesy, they are paid for the errors.
Yes.
Typically, Frank, so as one of the editors, you know that quite often, you know, astrophysicists sort of take the errors easy. Let me be careful here with wording.
That's a fine phrasing. That's a fine phrasing.
Okay, so and right now, yeah, over the last half an hour, we have actually seen how expensive it is to do the errors properly.
Correct. Yes, a lot of effort, tremendous effort.
Yes, thank you. And so we are right now at the page number, I think, 26.
Yes.
And you know what? I think that we can move to figure 19.
Okay.
And so we are right now we will discuss the impact of the source structure.
Okay.
And figure 19, I think that we can show. You know, what would we do? Why don't we zoom in the left part, and here we will just discuss the effect of the source structure on accuracy of determining the source positions. What Leonid has hidden from you?
Oh,
yeah. So he allowed me to tell you the truth.
Oh, please do.
Is that when we reconstruct the images, and actually the whole astrophysics of studying active galaxy at parsec scales is to reconstruct the images using very long baseline interferometry and then to study them.
Yes.
We enjoy being able to resolve the sources and to see details, and when we go to very high resolutions and millimeters, we can even see the black hole shadow, a wonderful result published in a series of papers in Astrophysical Journal Letters a few years ago.
Indeed, EHD, yeah.
But our colleagues doing astrometry and geodesy, they hate the fact that our galaxies on the sky are not delta functions.
Ah, well.
Okay.
That's true, they're not.
All right. So when VLBI astrometry reconstructs a source position,
okay,
a very important simplifying assumption is made.
Point source.
Okay? And this assumption is a point source.
Point
That's
source,
exactly correct. So anything what is different from a point source is negatively affecting the source position.
Sure.
Okay.
Yes.
And here on this example, on the left-hand side, you see a case when you have an active galaxy. So what is an active galaxy? What is actually an astrophysical object which astrometry is using to build the reference frames?
Yeah.
It has supermassive black holes in the center. We cannot see supermassive black holes, only their shadows at best.
At best.
It has accretion disk which is made from, okay, let's say dust and matter. We cannot see it in radio waves as well, but it feeds the central supermassive black hole, the central engine.
Yes.
And then through mechanisms which we do not discuss in this paper, but so we can talk about this later, probably not today. Through certain mechanisms, part of this matter falling down the central supermassive black hole, the one which is the most lucky, doesn't fall down and is accelerated away in the form of very fast jets of hot plasma.
Yes.
And that's what you see on the right-hand side here. On the left-hand side, you see another unlucky scenario when on the way between this object on the sky and us observers from Earth, there is a cloud of matter which scatters this material.
Uh-huh.
And instead of being able to see this very bright relativistic jet, you see this,
Halo.
who knows what.
Call it halo.
Some cloud on the sky. But it happens, it does happen because of a cloud of interstellar matter. So this scattering happens in our galaxy. Emission comes from another galaxy far away.
Yeah.
Billions of light years away.
Well,
But this emission is scattered in our galaxy, and it also affects our position. So positions of sources on the sky are affected by the fact that they are not point sources, but these are actually elongated jets.
Yes.
And what will be astrometry, and the region of this jet which is being measured by will be astrometry, or position of which is measured by will be astrometry, is the brightest region of this jet.
Okay.
Basically, apparent base, the starting region of a jet, which is the brightest, which is the most compact. This is the region for which astrometry measures positions.
Got it.
Everything else will shift this position a little bit, will affect this position a little bit in a not good way. And also when you are scattered, of course, this also affects your errors, not in a good way. Your errors grow. And that is what we discuss in this section of the paper. And we estimate the effect which astrophysics of the objects themselves and also astrophysics of propagation of radio waves
through
in the universe, basically in our galaxy, also affects our errors. And we tell that typically additional error, so part of the total error, which is related to source structure, so structure of relativistic jets and also the scattering, is typically below 50 microarc seconds. In the worst case scenario, it could be as bad as 100 milliarc seconds. If you're truly unlucky, it might be even worse. But a typical case, clearly below 100 microarc seconds.
Okay.
Leonid, are you satisfied? Are we moving on?
Yeah, and I think we can we can talk about images. And
very good. Wonderful.
Yeah, let's see some of those. So you want to go to one of the movies?
So one of the movies. All right. So movie number 3, I understand then.
Okay, tab and movies and this one. We are going to look.
Thank you very much. So let's start the movie. Okay, so this is the movie where you will see images of space objects changing one after another. But if you look at it, what you will typically see on these movies will be jets of relativistic plasma, which emit in radio waves. So this is plasma which moves with a speed very close to the speed of light. So typically, this the real speed of this plasma velocity is something like 0.99, 0.995 c speed of light. This is intrinsic real speed. If we want to measure its speed by following different features in the jets, and you will be surprised that some of these velocities you will measure to be several.
Superluminal.
Yes, 10, even in like 50, superluminal motion. But dear friends, this is the nature lying to you. This is a very fancy and very nice projection effect
Yes.
which is related to the fact that these jets look almost exactly in your direction. Typical inclination angle, typical viewing angle of the jet is 5 degrees.
Yeah. Okay.
Is it the case? Is it that most of the jets in the universe are produced so that they look in your direction?
I doubt it,
Oh, yeah, that would be fun. You know, all
but
the
I
jets
doubt it.
try to know where we are located. In reality, this is a very nice observational effect, a bias, which we have
Yeah.
to take care
Yes.
about. So this is the bias related to the fact that if a plasma is moving in your direction with a speed close to the speed of light, this emission, which is generated by this plasma blob, will be strongly beamed, or I will even use the word focused in your direction.
Yes.
So most of the photons which are generated in this moving plasma blob or plasma jet will go in your direction, and for you it will look like the jet is typically 10 times brighter than it actually is.
Right.
That is why when we observe sources, let's say 1,000, 10,000 so brightest jets on the sky, most of them, as a result of observational bias,
Yes.
will be the ones which look in your direction because they appear to be the brightest on the sky. Okay, and that is what you see on these images, on the screens. And so these non-point source structures are the ones which affect accuracy of astrometry. And this is also what is very exciting for astrophysicists to study.
Right.
As a part of this paper publishes astrometric results to source positions at the same time.
Yes.
As we have said, and this is extremely important in the beginning of this discussion, all our observations, both astrometric results, but also astrophysical results, we have made publicly available.
Nice.
So we provide all these images, which some of them are produced by us with Leonid, some are produced by other groups, and all of them are made publicly available by us, by other groups. So we have organized a collection of these images so that everyone in the world can access them and use them for their analysis.
Yay. Yay.
Yes, we are proud of it. But when I say we here, I'm not talking about only Leonid and myself. I'm talking about many scientists in the world who have contributed to that. Kudos to all of them.
Yeah, and we should mention that it's over 100,000 images. And but let's go back to a couple of words to add to what Yuri thought. Yes, we have images. We have photometry for almost all sources. We have about 1%, which we're missing photometry because we have too few observations. And we did not apply source structure contribution in our data analysis to put in line with prior analysis, and this ongoing work is not yet solved, and maybe in the future we will do it. But we have a good foundation for applying source structure contribution in the future. Several words about, we can stop this movie, several words about comparison with work of others. So there was another group used a subset of data which we use and called the catalog ICRF3, which was recognized by recommended by IAU. And
Frank, I think, sorry, Leonid, I interrupted you. Frank, I think that we can move right now to figure 20, which present comparisons between RFC and ICRF3, between the Radio Fundamental Catalog, the one which you have published, and the International Celestial Reference Frame.
Probably I would even not stay much about this figure. So but we look at possible. No, there's a different figure. We look at the different systematics.
Page 29.
29. Okay, thank you. Okay, hold on one sec.
We look at different systematics. So the main conclusion is, yes, there are sources and in the page.
There we go.
30. Yeah, so there's a distribution of the share of sources which position differences in significance on a given level. is it's mainly because of our model is different and is
Okay.
errors and in ICR3 was errors are too small, and we have evidence to show that our error model is more realistic.
Okay.
And
Okay.
there are some sources, next page, figure 21, which has significant structure. These are some extreme cases. Next page, you see sources, double sources, so with several companions.
Mm-hmm.
And in table 4, it gives
Okay.
statistics.
Okay.
So at distribution of the of errors. So and here we have reported errors. So that if you consider subset of sources with reported errors less than 1 nanoradian, which correspond to 2 milliseconds, this is a number of on ICR3 a little bit higher. But if to
Yes.
go if to grow this error limit higher and higher, then we see significant that RFC has much more sources.
Right.
And you can show movie number 2. Movie number 2.
To two?
Movie.
Oh, sorry, movie. Yeah. Sorry. Okay. Okay, so let's go to ICRF.
Yeah. So this is just shows this shows this. If you can start it, we will
Uh-huh.
show more. So it is distribution of the sources in ICRF3 catalog.
Come on.
Not running.
Why aren't we running? That's weird.
I think you need to hit a different button.
Hmm.
Not running. Ah.
Okay. Let's do
Okay,
it.
so since movie is not running, we can instead of we can show a figure in page 32, which basically is a similar figure, but for RFC. That's made the same way, but for radio fundamental
No
catalog.
idea why that one is not playing, but okay, let's go back to the figure
Yeah.
23. Sorry about that.
Page 32.
Mm-hmm. Cool.
So this is just a difference between two, and this because we used because this ICR3 group used only sources which they were campaigns they participated. Here we use all the data from all campaigns, no data point left behind. So this we have much more sources.
Little incompleteness down here in the southern parts.
Yeah, and the southern hemisphere, because here we have the northern part, we use this is mainly source mainly from VLBA, which is like the northern hemisphere, and south hemisphere different instrument. It's much more difficult to make observations, and we couldn't catch up progress with northern hemisphere.
But
So
otherwise,
you mentioned that.
But let's discuss it in a little bit more details here, but I will make it brief. So there is a dedicated, or there are more than even one, dedicated networks of radio telescopes which allow us to totally approach the southern hemisphere or hemisphere above minus 40 degrees declination. And the main instrument there is the very long baseline array of the National Radioastronomy Observatory in the US.
yes.
In the southern hemisphere, there are telescopes which are united in a so-called LBA, long baseline array, mostly located in Australia.
Yeah.
But the number of telescopes is less. But the most important is that they do different kind of science around the year, and only very small fraction of the time is actually devoted to very long baseline interferometry observations.
Got it.
So much observing time is available, and so that is why below minus 40 degrees declination, our completeness level and the density of sources on the sky is much lower. However, there is a very significant hope that things will improve relatively soon, because the square kilometer array is
SKA.
being built, SKA, is being built in Australia and in Africa, mostly in South Africa, and we are interested for this kind of work, for so-called SKA mid the network which will observe at centimeter wavelengths,
Yeah.
and this will be sort of the main, most sensitive station when put all together to drive the very long baseline interferometry to completely different level in the southern hemisphere. So
Nice.
scientists already know what to do, and they're already doing it in order to significantly improve the situation in the southern hemisphere.
Nice. Very cool. Very beautiful.
Let's jump to page 33. So that we're talking about astrometry, about accuracy, but what are errors?
Yes.
And errors are, we can characterize by one, and we can show this plots. Yeah, we can characterize by one word. So it because it varies on over almost 4 orders of magnitude. So therefore we just put a distribution, a cumulative distribution of semi-major, semi-minor axis, and on the right hand side it's just a zoom.
Right. Of the gray area.
So this distribution. So
Yes.
it just shows, and if scroll down a little bit and look at the page table 6. Sorry, table 6. So it gives quartiles of the semi-major position errors. So so we see if that the median is 1.3 milliarc second. Although at the fraction of source of 25%, they have half a milliarc second.
Okay.
Next page. What is the origin? So why we have? It turns out that position errors depends on number of observations, number of observing sessions.
Yes.
So it's just dependence on the a number of scans. So in radioastronomy, we call scan a period of time when we observe a given source. We antenna scans, they track the source. So that is it. If number of scans is too small, that position errors is large. And I can cite similar on number of observations.
Okay.
And from the other side, when we see that the number of scans and number of observations approaches some limit, there is no further growth of errors because in the left part, the errors are dominated by thermal noise. So therefore, more observations, more scans beat the thermal noise. But when we hit the floor related to systematic errors, so that errors cannot improve further.
Cool. I'm with you.
We can move right now just for a second to the figure 28, which is just below these ones.
Yeah.
And here on figure 28, yes, we can immediately see the comparison between source density. You see below minus 40 degrees declination and above, and you see the difference when you devote a VLBI network.
Right.
You know, to different a lot of different science observations. So here in the south, the source density is 4 times.
Yes.
3.5 times lower than in the north. But once again, we promise we will improve relatively soon.
I'm gonna hold you to that. I'm gonna hold you to that, Yuri.
But I don't hold my breath. But if you jump to page 38 and look at the figure 30, related figure 31.
Okay, that's good.
That figure 31 provides a probability to find a calibrator within a given distance target calibrator separation. So what is the 3 colors?
Okay.
For red, it is for C band, green for X band, and purple for K band.
Okay.
Purple, I put it just for comparison. It was not K band was not targeted. We target X band.
Yes.
And we say that probability to find calibrator is about 99% within 2 degrees. So it means mission accomplished.
Yay.
We promised to do that. It took 30 years of observations, 25 years of work, 4 or 5 years of world-time data analysis, and we delivered that.
Very cool. Congratulations.
I can mention, probably we don't need to go into the text, but we made associations with the major surveys. So with Guy we have 60% fraction, Pan Stars 76%.
Pan Stars.
This probably we for 40% of sources we determined jet angle using images. From literature search, from NET, we found redshift for 40% of the sources.
Leonid, also, I think it is important to mention X-rays. So I think
Yes,
that
and just what I wanted to say
okay,
that recent catalog Irasita association fraction is 56%.
Right.
But this is we just put table. We didn't make interpretation. It is subject of next publication.
Frank, I believe right now would be a good moment to go to page 44. I hope that Leonid will be fine with that because this is the main result of this work.
Correct.
So if our listeners or our viewers survived until this moment, so this is the subject of the paper. So the paper presents the catalog, and you don't even can see the catalog here. What you see here is description.
The metadata. Yeah.
Inside the catalog, and even description doesn't fit into the whole page. So there are 44 columns which present all the results of this work, including positions of the sources, the errors, which I trust now you believe us is more important than position.
It's more important the actual measurement.
Yes, and many other things, and also it has information, basic astrophysical information about the level of emission which we see from parsec scales from all these objects at different observing bands. I think between 2 gigahertz and 24 gigahertz. Yeah. So when this means that people can immediately use this catalog not only for direct absolute astrometry as a reference frame, but also for differential astrometry if you want to measure your position relative to something
Right.
we have published here.
Cool. Beautiful.
At the end, Frank, if you can play movie number 1.
Sure. Let's go back to the movies and hopefully they will play. So let's try, you want to do the this one?
Yeah.
Let's roll this one.
It's plays. Yeah. Concerning continuation in the future work. Although paper appears this month, results were made public starting from 2009 and updated on a quarterly basis. And here you see updated. If you look at this low left corner, you see this data updated on quarterly basis, and we made first update after publication a month ago, and we have intention to continue on the quarterly update indefinitely.
What does it mean indefinitely? Are you planning to? Do you already have solved the problem of living forever?
Well, he's got the errors figured out anyway.
We'll see.
Very good. Beautiful. And the other thing that we want...
so this also some backlog of images for different for second and third epochs, which is in our processing queue. So there will be more images. And with quarterly update, usually we also make some improvement in data analysis strategies so that it's evolving project.
Yes, and we should mention here that you can also get it here from the website. You can pull down the positions and all if you want from the NASA website, or you can pull it off the journal article. Anything else over here?
If you go to the NASA website, this is exactly the place from which these quarterly updates of the catalog will be made available.
Nice. Yep. Through 2024, 1203. So the next quarter will be coming up. Very nice. Ooh. Ha. Very cool. I like that one. The growth of astrometry. Okay. Let's head back to the article. Bang.
So I think, Frank, that so Leonid, are we done with describing the article? Because sort of we finished the story with the catalog.
I'm not sure that anybody on the world is in a position to continue listening us.
Okay. We are done, Frank.
All righty, we'll call it. So Leonid And Yuri, I want to thank you so much for walking us through your very awesome and exciting article on a fundamental part of astronomy. Okay, so it's very cool. Very nice. Let's see. And you kind of mentioned it several times as we kind of went through. So I'm going to invite you to expand upon that a little bit. So where do you think we go from here, given the published article? We're going to have quarterly updates. That's fine. Even the title of the paper has a 1 in it, so you might expect there might be a paper 2 or paper 3, et cetera, et cetera. And are there other bands, other observational bands that one may consider doing for these? So just sort of in general, where do you think we go from here, given the published article?
Allow me to say a few words about the article number 2, because the draft, or at least the plan, and even the draft already exists.
Cool.
So the plan is to have the article number 2, the same radio fundamental catalog number 2, and then we'll see what the title will be. But the working title is number 2, Astrophysics.
Cool. Okay, that's nice and broad.
That is why I worry a little bit about the title. It's already 4 words, so not that bad. So the plan there is to use the data which we, and again by we I mean not just 2 of us, but many people around the world have collected throughout the years, observing extragalactic radio sources, which are active galaxies with jets, relativistic jets. So by using all this data in order to study observational and physical properties of these jets at parsec and sub-parsec scales. I'm not going to give right now the second story about the paper, which is not published yet. We'll just say 2 things. So important for us. So 1 thing, we will study astrophysical properties. 2, why do we want to do it? To understand how these jets are born.
Yes.
How particles are accelerated, and how do they proceed, so evolve through time, through distance, their evolution. What are their observational properties? And number 2, which is extremely important, we need specifically to understand completeness characteristics of our sample.
Yes.
We have mentioned today that if we have any sorts of biases in our data and we do not understand these biases, there is a risk that we will get a wrong answer by analyzing the samples, collections of sources on the sky.
Yes.
So a very important component of this paper will be to understand what is the level of emission, the level of radiation, a cutoff level to which we managed to find all active galactic nuclei on the sky. Okay.
Cool. Nice.
So is it 1 Jansky? Is it 100 millijanskys? Is it 50 millijanskys? So this is the question which we will answer, because this will allow not only us to then properly perform astrophysical analysis of this data, but it will also allow us and everybody else in the world to perform new studies by properly selecting samples of extragalactic sources of active galactic nuclei with well understood characteristics, without any risk, or without a risk to incorrectly interpreting results later. And another point here is also that completeness, understanding properties of your sample, is extremely important when you not only assess your errors, but when you perform the studies to understand significance of your results.
Yes, right.
In order to assess significance of your results, you need to work with complete samples. And it is right now very important also for some of the studies which we are doing right now, performing multi-messenger analysis of active galactic nuclei, comparing their electromagnetic radiation with their neutrino radiation. And there is everything about statistics, is everything about being able to properly assess significance of your results. And without understanding completeness characteristics of your samples, you simply cannot do that.
Concerning a further observing program, we don't think that for next 10-15 years there will be significant progress, not because we are so smart, just because we approach to the limit of planet-wise resources. Just for the observing programs which we discussed in this paper, it took 2 years non-stop observing time as will be. So therefore, a substantial increase of the sample, this factor of 2, will be feasible only after new instruments like NG-VLA and SK will start to work. So therefore, further observations will be mainly focused on some follow-up, to looking for some interesting sources. And again, the data which already collected provides very rich material, which is publicly available, and we hope not only we ourselves, but other members of the astronomical community will be using that material, because in our work, as we decided from the very beginning of our collaboration, 2003, we use only publicly available data and publicly available results. We don't hide anything. And nowadays at NASA, it requires policy, which became effective 2 years ago. We are required to do that.
But Leonid, allow me to rephrase it in a positive way. So Frank, it is easy to see that we are Russians and we are sort of, it is typical for us to phrase the things negatively, but by years it have trained me that you can phrase everything also positively, and I enjoy it, if I may. So
either is fine with me, it's fine.
But still, the positive claim is, so SKA and NG-VLA are coming up.
Yeah.
And they will provide the next big step towards improving the celestial reference frame.
Awesome.
Okay.
I like both perspectives, positive, plus and negative. It gives you balance, Leonid, Yuri, I want to thank you so much for walking us through your very awesome and really fundamental astronomy paper. So really nice job. It's beautiful work. Thank you so much.
Thank you, Frank.
And that will do, everyone. And I hope this made your positional astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Thank you.
Bye, Frank.
Bye.